Hello everyone, welcome to another particular lecture. This is the lecture 17 and this is the last lecture of our conformers. And in the previous lecture we discussed about the cyclic conformers. So here we are just extending our cyclic conformers thing. And here in this particular lecture we are talking about cyclohexane and decalin system in elaborate way. Okay. So first of all let us talk about cyclohexane. So cyclohexane is a very unique molecule in terms of uh, stereochemistry or conformational analysis. So here it is a six-member ring structure similar to benzene, but it is not a benzene structure because here all the carbon atoms are in sp3 in nature, and since it is a ring structure, then obviously it contains some kind of angle strain and ring strain. And if you think closely, here if you see closely, so this particular bond angle is 120 degree, and this is way more higher than our prescribed sp3 bond angle, that is 109.28 degree. And that's why actually cyclohexane doesn't present in this particular planar form. It present in three different structures. Okay, and out of this structure was very important for us. So here in this particular structure, if you see, this is called the chair structure, and this particular structure has been observed to actually eliminate the bond angle strain here. So it is 120 degree. Here the bond angle strain is minimized, and due to this particular representation, the cyclohexane molecule become non-planar in nature. Okay. So the chair form is the most stable form among all the cyclohexane form, these two. Okay, and this particular cyclohexane chair form is nothing but free from torsion strain and angle strain, but it is a little bit of rigid than a boat form. And the boat form is something like this. This form is the least stable because of the two eclipsing strain present between these two hydrogen. Now, these two hydrogen are actually in a closer vicinity, and due to this particular thing, there is a eclipsing strain present, and also this is present in the 1/4 position. So there is a 1/4 diaxial strain is there. Okay, and actually that's why this particular chair conformer become much more stable than boat conformer. And also there is an intermediate a structure was there between a cyclic conformer and the boat conformer that actually scientists describe about the twist boat system. This is the in between chair and boat conformer. So if we go for the energy profile diagram, then chair should be here and boat should be in the above area. And the twist boat structure is present somewhere between here. So this is the general energy profile diagram of different kind of cyclohexane derivatives, the different kind of forms. Okay, so now here actually the most important structure is the chair form. So we are much more discuss about the chair form first. So here if you see the chair form, you can find that there is a two different type of bonds there. So okay, so here two different type of bonds present here. One is the axial bonds, which is depicted in this particular blue bold bond, and the black bold bond are suggest the equatorial bond. Now in normal temperature, what happened that these two particular bonds are indistinguishable to each other because due to the low energy barrier, as we know that in conformers there is having low energy barrier, so these two are actually interconverted, and that's why in cyclohexane case in normal temperature NMR spectroscopy we get only one NMR spectra, whereas in low temperature the ring flipping due to the axial equatorial exchange is very less, and that's why actually these two will generate two distinguished signals in NMR spectroscopy, especially in low temperature NMR. It's minus 40 and minus 60 degree temperature. We get two different spec. Now here you can see the interesting thing, like some are the axial bond and some are the equatorial bond. Now here if we see our parent structure here, so the all above the plane bonds are depicted in the red hydrogen. Here you can find that all the axial bonds doesn't contain the red hydrogen. That means that all the axial bonds are not equivalent to the bond that is near to the observer. like all the bonds that actually present in the upward direction, like this one, this one, this one, this one, this one, and this one. These all bonds are upward position, irrespective of the bond which are present in the axial or equatorial bond. They are actually depicting the closer to the observer bonds, like the bold bonds. So here actually I was emphasize this particular fact because in where I was in graduation, actually I made a mistake here. I misconceived that all the axial bonds contains all the groups that are actually near to the observer, but it is not. Like axial bond having their own unique properties, equatorial bond having their own unique properties, but all the axial bond doesn't depict the bond which are near to the observer. Okay, so that's why this figure is very important. So please note down this particular figure and don't make the misconception that all the axial bond having the group that is near to the observer. Like all the bond that actually towards upward direction, then this particular bonds are actually contains the particular groups that is closer to the observer or present in the bold bond, and the dashed bond group are actually present the bond which are actually lower down, facing in the lower down region. Okay, now we have to look much more details about this particular thing, but before that we are talking about the ring flipping nature. Okay, so basically cyclohexane having a property to flip the particular ring, but before that we are looking for some kind of facts here. So here there is a cyclohexane parent follicle that I am discussing in the previous slide, and this will stay here in the chair form, and the bond contains red hydrogen, like the all X are, so the bond contains red hydrogens are called beta bond, like the bonds which are actually towards the upper direction, then this particular bonds are called as beta bond, whereas the bonds actually contains the black hydrogen, that means the below of the plane of paper or away from the observer bonds, are actually called the alpha bonds. And the cyclohexane contains a C3 symmetry element. Okay, and here in this figure you can find that the bond denoted in the blue are called the axial bond, and the bond rest or the denoted in the black color is called the equatorial bonds. And you have to draw this particular structure, and the easiest way to draw is first make these two and join them, and you make a cyclohexane. Simple. Okay, this is how you make the cyclohexane chair form. And another interesting thing is this particular ring is have a tendency to undergo ring flipping, and the ring flipping is nothing but that axial bond convert interconverted to equatorial bond and vice versa, and this is actually happen in the room temperature to obtain the extra stability. Like in the case of normal cyclohexane, the extra stability is not observed right now, but when we are discussing about some kind of substituted cyclohexane compound, then you can find that this ring flipping is very important to gain the extra stability of the cyclohexane conformer. Okay, and the ring flipping can be pathway in two pathway, in C2 pathway or sigma plane pathway, like from either this way or the plane pathway. And an interesting detail that will be observed, that after ring flipping, before ring flipping, this particular carbon is your first carbon, but after doing the ring flipping, you can see that this particular carbon is now present in the adjacent position. So when we are actually flipping the ring, then the carbon center position has been shifted to their adjacent position. Okay, so this is the attention to detail you have to check here. Okay, so now let us discuss about some kind of substituted cyclohexane. So here, if we it is the normal cyclohexane here. Now what happened that we change this hydrogen to a bulkier group, there is a methyl group. Now here interesting thing is, methyl group here, if it is present in the axial bond, then what happened that this particular axial bond contains hydrogen, this particular contains hydrogen. So what happened that here this having their own electron density, this having their own electron density. Similarly, methyl having their own electron density. So here one kind of flag pole interaction is observed. This is called a diaxial interaction, and diaxial interaction is observed when any bulky group present in the axial position will face the 1,3 diaxial interaction. Okay, and also you can find there is a 2 Gauge butane interaction is also there. Like, you know what is the Gauge butane interaction in the second class itself. I was discuss about the Gauge butane interaction. So here we are just, let us find that where is the Gauge butane interaction here. So this figure is actually self-explanatory. Here you can find that this particular methyl 1, 2, 3, 4. So this is your 1 Gauge butane interaction. Here is your 1 Gauge butane interaction, and this particular black color bond are actually your second Gauge butane interaction. So if we see the substituted cyclohexane, there is the 1 methyl cyclohexane compound. Okay, so in axial conformer, what happened? This particular conformer having a diaxial interaction, also into Gauge butane interaction. That's why this particular conformer is present in a least stable form in room temperature. But if the particular conformer is undergo ring flipping, then you can find that this particular CH3 now present in the equatorial bond. And since it's present in the equatorial bond, that means there is a no diaxial interaction present now. Okay, so no diaxial interaction present here, as well as there is a no Gauge butane interaction, like there is a no two particular CH3 group present in the 60-degree vicinity. That means no diaxial interaction and no Gauge butane interaction. That means this particular equatorial form is much more stable in the room temperature. Remember in previous slide I am discussing that in case of cyclohexane, that ring flipping both of the structure having the equal energy, that's why there is a not that much significant ring flipping in case of cyclohexane part. But here, since we are actually substitute your one of the particular group with a bulky group, then you can find that how the ring flipping comes into the play to determine the stable conformers. Okay, now we are discussing about disubstituted cyclohexane, that is the 1,2-dimethyl cyclohexane. Now this 1,2-dimethyl cyclohexane can present in the two different form. One is the both are in the cis form, that is the both are present in the same direction, or the when the both CH3 present in the bold bond, and one present in the trans form, like one is the away from the observer and one is the near to the observer. Okay, so what happened that in substitution cyclohexane, if I talk about this particular part, the cis conformer, so here what happened that this particular CH3 will again undergo the 1,3 diaxial interaction, and if you find that this particular CH3 contains 3 Gauge butane interaction due to presence of 2 CH3, one is very much clear. This is the one Gauge butane interaction, and if we find another Gauge butane interaction, then you can find that this particular thing is another Gauge butane interaction, 1, 2, 3, 4, and this angle is 60-degree, and the figure is little messy right now. And if you find another Gauge butane interaction, this is 1, 2, 3, 4. So this will be your third. 1, 2, 3, 4. This the black color denoted bond is the one Gauge butane interaction. This black to red is the second Gauge butane interaction. Similarly, this black to blue is the third Gauge butane interaction. So the axial form we got this. Similarly, if we go for the ring flipping, then it also one of the methyl group present in the axial direction. That means this also contains a 1,3 diaxial interaction right now. Okay, as well as this also having the three particular GBI, 1, 2, and the red one, 3. So what happened that here, so what happened in here, in both of the cases, after ring flipping or before ring flipping, the both of the conformer having the same kind of strength, like 1,3-diaxial interaction is also there and similar kind of GBI or Gauge butane interaction present. That means both of the conformer are equal stable. Okay, and since this particular conformer doesn't have any kind of plane of symmetry, that means we can say that this is the chiral compound, but it is a optically inactive compound. Now let us talk about the trans compound. Like if we look about the trans compound, see in normal scenario, the both CH3 present in the trans to each other, and the both this contains also diaxial interaction. This particular CH3 will also face in diaxial interaction, as well as there is a 4 Gauge butane interaction present here. Okay, so 1, 2, 3, 4. Just let me show you where the 4 Gauge butane. 1, 2, 3, 4. This is the 1 Gauge butane interaction. Similarly, 1, 2, 3, 4. This is another Gauge butane interaction. This is for this particular 2 CH3. Similarly, this 2 particular CH3, uh, there is a 2 Gauge butane interaction. This is the 1 and this is the 2. Okay, so there is a 4 Gauge butane interaction there, and also extreme diaxial interaction for the both of the CH3 group. But if we do the ring flipping, here the diaxial interaction is not there and only 1 Gauge butane interaction present here. That means this particular equatorial structure, both equatorial di-equatorial structure, is most stable in the case of trans dimethyl cyclohexane. Okay, now we are moved to the 1,3-dimethyl cyclohexane. Now first we are talking about the cis 1,3-dimethyl cyclohexane. Now in normal case where the diequatorial, this is called the diequatorial conformer. So in diequatorial conformer you can find that there is a no Gauge butane interaction present here, as well as a no diaxial interaction present there. That means this particular conformer is highly stable. Whereas here in diaxial conformer you can find that there is a methyl-methyl interaction, 1,3-dimethyl interaction is there. Mm, okay, and this is the extremely disbalancing force there, and also there is a 4 Gauge butane interaction there. That means this particular conformer is extremely unstable, so the equilibrium has actually shifted to here, this particular conformer. That means the diequatorial form is extremely stable in the case of cis 1,3-dimethyl cyclohexane. But if we talk about the trans 1,3-dimethyl cyclohexane, here you can find an interesting thing where the both of the conformer, whether it is the axial equatorial or equatorial axial conformer, okay, both having the same energy because of the same amount of diaxial interaction as well as the same amount of Gauge butane interaction. That's why the both of the structure is actually equivalent in the case of room temperature, low temperature NMR. Okay, and it is a chiral molecule, and these two particular molecules are actually homomorph to each other. Now let us talk about the very interesting, that is cis 1,4-dimethyl cyclohexane. This is a very interesting thing. Like here, the axial equatorial case where the both are the in the same way, like both are the present in the upward direction. That means this is a cis compound. Like after doing a ring flip, we can find that these two both compound having the same number of Gauge butane interaction. It is a 2 Gauge butane interaction, and also due to this one methyl present in the axial position in both of the cases. So what happens is there is a diaxial interaction is also there. That means this particular compound having the same energy, and it is an achiral molecule because if you see here, this particular plane is present here, and due to this particular plane of symmetry present, that means this particular molecule become achiral in nature. In the case of trans 1,4-dimethyl cyclohexane, the di-equatorial are much stable because it is no Gauge butane interaction present there and no diaxial interaction present here. But in the case of cis compound, you can find that extreme diaxial interaction present here as well as the 4 Gauge butane interaction present here. That means this particular uh, conformer is much stable in over this particular diaxial conformer. Okay. Now let us tell about the summary, that what is the final summary of the substituted cyclohexane stability. Like if it is a monosubstituted cyclohexane, there is the 1-methyl cyclohexane or any kind of compound, then we can say that the preferred conformer is the equatorial conformer where no Gauss-Butane interaction is there. But in the case of 1,2-cis dimethyl cyclohexane or 1,2-cis substituted cyclohexane, then equatorial axial conformer getting much more preferred or much more stable over the axial equatorial conformer, and number of Gauss-Butane interaction is 3. Similarly, in 1,2 trans, the equatorial conformer is much more stable and 1 Gauss-Butane interaction is there. 1,3 disubstituted in cis compound, equatorial is stable where the 0 Gauss-Butane interaction is there, but and 1,3 trans, the equatorial axial is much more stable, having 2 Gauss-Butane interaction. And 1,4 cis and 1,4 trans, for the cis case, equatorial axial conformer getting higher stability over the other conformer, and the minimum Gauss-Butane interaction is 2. And 1,4 trans, the equatorial is much more stable, having the Gauss-Butane interaction is 0. So this chart is very important because sometimes there is a direct question, MCQ question comes from this particular chart. So you have to remember this particular chart. Okay. Now let us discuss about the hydrogen bonding stability in cyclohexane conformers. Okay. So if there is a 1,3 dihydro or 1,3 substitution, there is a 2 OH group present. Okay, so what happened that this particular diequatorial, although this particular diequatorial are much more stable, like in the chart itself we can say that 1,2-cis compound having the equatorial conformer is much more stable over diaxial conformer, but if there is a 2 OH substituent is there, then the diaxial become much more stability due to the presence of intermolecular hydrogen bonding. Okay, and in the same case, if the 1,4 substituted cyclohexane, if there is a OH present, like here 1,4 cis conformer, the equatorial axial is much more stable in chair form. But if there is a 2 diol substituted is there, okay, so what happened that this particular chair conformer become not much more stable, like this will flip to the boat conformer, because in the boat conformer we learn that 1,4 the 1,4 diaxial group become the closer vicinity, and this closer vicinity will allow this particular group to do an intermolecular hydrogen bonding, and that's why here the boat conformer getting much more stability over this particular chair conformer. And the driving force to conversion of chair to boat and further twist boat is due to the hydrogen bonding, intermolecular hydrogen bonding. Okay. Now there is another interesting thing that is observed in the case of glucose type of molecule, that is called the anomeric effect. Anomeric effect is a stereoelectronic effect that the heteroatomic substituent adjacent to an heteroatom within a cyclohexane ring to prefer the axial orientation instead of less hindered equatorial orientation. Like if any kind of this particular sugar type of thing present where the oxygen group is present there, or any kind of heteroatom substituent present there, so its adjacent bond, we know that in cyclohexane part uh, this equatorial is much more stable over axial, because in case of axial there is a 1,3 diaxial interaction is always present. Okay, but in the case of this type of compound, like apart from this particular 1,3 diaxial interaction, this axial structure getting the highest priority over the equatorial structure, and this particular thing is called the anomeric effect. Now this is mainly observed in the sugar chemistry, and this particular we know that the axial bond is called the beta bond, that is the present in the above or near to the observer, and the lower bond is called the alpha. So here this particular is called the alpha anomer, and where this particular group is the called the beta anomer, and the naming is determined that OH group present in the which bond. Here the OH group present in the alpha bond, that is it is called the alpha anomer, and here the OH group present in the beta bond of the cyclohexane group, then it is called the beta NMR. And here among of this particular thing, alpha D glucose having the much more stability over the beta D glucose. So we can justify or we can prove the stability of anomers by using these arguments. Like the first argument is the dipolar stabilization. Like when here the heteroatom present here and here also an hetero group present here. So if the case of both the equatorial conformer, then what happened that but this compound having their own dipole, this also have their own dipole and both are in the same direction. So that's why the resulting dipole is much higher, which destabilize the equatorial structure. Whereas in the case of axial conformer, this dipole is acts here and this dipole is works here. So that means the both dipoles are works in nearly in opposite direction, or the angle between the direction is very much high. And that's actually what happened, that this particular angle actually decrease the overall net dipole value. And that's why actually this particular diaxial conformer is much more stable over equatorial conformer. Okay, there is a next argument is the electrostatic effect. Like if we just draw this particular structure in the Newman projection formula, then we can found that this oxygen, this bond is the oxygen, and this oxygen contains the two lone pair, and we know that lone pair takes the much amount or much electronic area, like lone pair repulsion that we have learned in the chemical bonding part. And here this lone pair takes much more electronic load, so this particular adjacent group within the equatorial structure makes this particular steric repulsion. Whereas in the case of the diaxial or axial structure, this particular steric repulsion is very less, because here the hydrogen group is there, and that's why this particular structure better much more stable over this particular part. And another argument is the stereoelectronic explanation. Stereoelectronic explanation says that when the diaxial form is there, so the lone pair are actually attack here, and this particular OH group or OR group the present here is actually leaves out and makes here in a double partial double bond characteristic. And due to the formation of this partial double bond characteristics, this particular structure getting highest priority. So that's how we are actually justifying the anomeric effect in the case of cyclohexane structure or uh, like this type of substituted cyclohexane structures. Okay. Now there is another thing, there is a keto compound stability by anomeric effect. So this type of compound are called the keto compound. Now what is the stable form of this particular compound? Let us discuss about the two chair conformer. Here you can find that this particular for the case of this particular oxygen, this becomes there is axial bond and this become an equatorial bond. So here in axial bond of this particular oxygen, this particular heteroatom present here, that means for anomeric effect is justified for this particular oxygen. But if we look about for this particular oxygen, the axial bond is this and equatorial bond is this. That means the anomeric effect justified for this particular oxygen but not this particular oxygen, because here the heteroatom present the equatorial bond. Okay, that means here one anomeric effect is justified. But in the case of here, you can find that for this particular group, okay, so this become axial bond and this become equatorial bond. So the heteroatom present in the equatorial bond. So here no anomeric effect is here. Similar case in oxygen case, this is the equatorial bond and this is the axial bond. So here also equatorial bond contains this particular oxygen. So this will the least stable conformer, that is no anomeric effect for both of the oxygen case. But here in this particular structure, you can find that this become an axial for this particular oxygen, and this particular bond are actually present in the anomeric effect. So anomeric effect is justified for this particular oxygen. Similarly, if we look about this particular oxygen, this become the axial bond for this particular oxygen, and this becomes the equatorial bond. And for this oxygen, this hetero group present in the axial position, means this both of the ring, red ring or black ring, both of the cases the anomeric effect is justified. That means this is the most stable, and hence the stability order is this. Then this particular where one of the oxygen's anomeric effect is justified, and the least stable is this compound, where there is a no anomeric effect is observed in both of the ring. Okay. Now let us talking about the last part of our conformational analysis, the chemistry of Decalin system. So Decalin system is something looks like this. Okay, so Decalin present in the two different form. One is the cis Decalin, where the both of the group are present in the same vicinity, and the trans Decalin. So here actually we can find that these two are Decalin system, and if we go for the Chiar conformer, you can find that this particular cis Decalin present is something this type of structure. Okay, and whereas the trans Decalin, where the both are in the proper Chiar conformers. So that's why the trans-decalin having the more thermodynamic stability over the cis-decalin because of this particular structure. And due to this type of structure, it contains the three Gauge-Butane interaction. But here in the case of trans-decalin, there is a no Gauge-Butane interaction is present. But what happened that in the case of trans-decalin, it is a rigid system, whereas this compound are actually not that much stable. That's why it is a non-rigid system. It try to getting the greater stability, and to try to getting the greater stability, the cis-decalin has the tends to ring flipping. But in the case of trans-decalin, since it is a rigid molecule, that is the no ring flipping is possible here. So this is the basic thing about the decalin system. So with this, we have to end this particular lecture, and with this also we have end our conformers in detail. So in the from the next lecture, we are for this stereochemistry part, we are discussing about the asymmetric synthesis part. So in the lecture, we are discussing about the cyclohexane, substituted cyclohexane, anomeric effect, cyclohexane stability, and decalin system. So I hope it will be clear for you. So thank you for listening.